Hey everybody, it's your boy Chili. Welcome back to Hardware 3D. Well, let's just jump right into it. In the last video, we'd gotten cube shadow mapping working to a certain degree, but if we look here, obviously there's still some crap that is messed up. And this video basically just going to be going over the steps I took to try to figure out the problem and rectify it. So, yeah, where should we start off with? I mean, I could just tell you guys what the problem was and how I fixed it. Jump straight to the chase, but I figured, you know what? Might be a good opportunity here just to go over some ideas, some techniques for debugging, just what I actually, the steps, the process I actually went through to find the problem and fix it. So, we got this stuff here. It's a problem. Now, usually when I've got graphical errors like this, I might try to stare the code down for a bit, but when I'm stumped, what I'm going to do is I'm probably going to bring her into the graphics debugger. I'm going to step through the shaders, and specifically what I'm going to be stepping through is the stuff here, the stuff that does the sampling of the shadow map and the comparison sampling. The problem with this, though, is that it doesn't give us very much information, right? The sample compare level 0 basically just tells us whether something is in front of or behind the previous depth in the shadow map. And what I really want to be able to do is I want to see, okay, what value is coming in from the shadow position, and I want to compare that to the value that I'm sampling from the shadow map. We don't get that here. So my first step in debugging this thing is I don't just want to sample compare level 0. I also want to sample just the value in the depth map, in the cube map. So I'm going to sample that. I'm not going to use it for anything. I just want to use it when I step through in the debugger. I want to be able to, inspect that, see how it compares to the depth that we get from here, or the distance really, from the shadow position. Now the problem is that with our current sampler, we have a comparison sample state. You can't use a comparison sample state to do a normal sample. So I've got to add another sampler state in here. And in sampler, now because we're going to have multiple samplers, I need the ability to specify what slot the sampler binds to. So I put that in there. And in the Lambertian pass, I add a line of code in here that is going to add another sampler. You might be wondering why I have this if statement in here and what's all this about. And this is basically just some stuff I added in to make sure that this value would be available in the debugger. Because I noticed that if you don't use a value, even if you're not in optimization mode, once you pass the point where that value is no longer in use, it becomes unavailable in the debugger. So I just made sure that I use it somewhere. So we're gonna run this under graphics debugging. So we can choose a pixel that's right on the edge of the artifact here. And we'll step over this stuff, doesn't matter. We want to step into the shadow function, and want to step into here. All right, so our length, which is basically our depth value, we're going to get that. And that is going to be 8.65. Next, we're going to sample from that shadow map. And we see that it is 0.01. Now, you got to remember that in actuality, the depth value is the length divided by 100. So if we divide this by 100, we see that it is going to be 0.008. And this one is 0.01. So the depth map thing is significantly in front of this length here, which means that it is going to be detected as being in shadow. So that part makes sense. The part that doesn't make sense is, okay, this value in this depth map, it should be about 0.008. I mean, it's possible that this length here could also be wrong, that we're calculating. It's unclear at this point, but there is some disconnect between them because they should be very similar because they're both being generated by the same surface. Now, another tool that we can rely on that we have here is the ability to dump our shadow cube map to a bunch of images. So let's try that out here. We're going to put ourselves back in about the same position. Doesn't really matter where we are. It doesn't matter. It only matters where the light is for this one. But let's see if I can find, yeah, shadow dump cube map. So we'll do that. Close out here. Now, if we look, I've got a bunch of changes, and that is the shadow maps. So we can see here, this one looks, I don't know, sort of okay. Not really. It doesn't really seem okay if you think about it, but nothing super jumps out at you. What about the one in the actual direction? Okay, so this is interesting, right? This white band here, what is generating this? And if you think about it, you got this white band here in this direction. This is the direction that we had one of our artifacts in. So you might think there's a good chance that there's a correlation between this and the artifact, right? Because this should be the closest thing that you see. It should be the darkest color, but it's full white. It doesn't make any sense. This one makes sense for full white because there's nothing up here, so it should be white. This one, yeah, that's part of the ground. This is facing maybe to the right. And again, facing to the left, we had another artifact, and we see another white thing here. So right now, I'm thinking, okay, this is probably where things are going wrong. This is causing our issue. But what is causing this white? I don't know. And my next step in trying to figure that out was basically just to simplify the geometry of the scene, cut out as many things as possible, keep it simple so I can reduce the number of things that could possibly be impacting this. And yeah, just make my life easier for narrowing down what the problem could be. So I cut everything out except for one test cube. So the first question is, okay, now with this new simplified scene, can I reproduce? Well, first of all, where's my light? It's actually, I believe it is inside of the cube. So we're going to move the light up here. And right away we can see, okay, we're not going to have a problem reproducing this issue. I mean, we don't know if it's the same issue, but it looks like it's probably the same issue here. So we've got our artifact here. All right. Well, then let's see what our cube map dump looks like. Looking at cube map dump. Okay, here is one corner of the cube. Here is another corner. Here is some kind of flat surface of the cube, and here's the edge of the world. Here's another face of the cube. So it's not looking like we have any of those weird white sections that don't make any sense. That's what I'm getting from this. All the white sections seem to correspond to, you know, empty space, the void. That makes sense. So let's take a look at this one in the debugger. I'm going to capture a frame. Take a look at a pixel just outside of the dead zone there. Shadow position seems plausible. Y is below, right? Z is positive, X is negative. That seems to correspond with the orientation that we have it in. I'm going to step into here. We are going to get the length, which, yeah, that seems about right for those distances. We are going to get the sampled value, 0.035. So these are very close once you divide by 100 to normalize the length here. We see, okay, yeah, this is about right. It's just barely passing the test. Now, if we move that to just inside of the dead zone, and we do the same song and dance, you're going to see very similar shadow positions because we haven't moved all that much. Step in, length, yeah, 3.5. It's about the same as what we had before. We check this length, 3.3. So now the shadow mapped distance is closer than the distance that we are rendering, and that means that it is detected as in shadow. But it should not be. That's not how it works, right? Because there's only one piece of geometry generating both the shadow and this calculated shadow position. So they should give very similar values. Of course, there are some errors, and that's why we have biasing. But this isn't the kind of error that you would expect from, like, you know, texture sampling error or floating point error. It's a very weird shape of the error here. This circular shape, which sort of makes sense when you think of we're using distance. The formula for distance is the same as the formula for a circle, right? Pretty much. So there's correlation here, but there's a problem with the calculation. Is it the distance, the actual distance calculation is just the length function, right? It can't be wrong. So there's got to be something wrong with how we're generating our shadow map. I mean, when you're debugging, you should never be like, there's got to be this or it's got to be that. You should keep your mind open because it's easy to tunnel vision and miss something. But it is a good, you know, working hypothesis for the moment that the problem is probably in the generation of our shadow map. Now, basically, it's at this point in time that I realized, okay, it's not like some big discontinuity like we saw in the previous. When we had the big scene, we had the big white section that didn't make any sense. Here, we're not seeing that. We're seeing a continuous change in values, and at some point it crosses a threshold and we enter the dead zone here. And what I want to do is I want to be able to analyze those values in a little bit more depth. And our dumping of our cube map images, it's not going to allow us to do that, because when we dump, we convert a 32-bit floating value into an 8-bit integer value. We don't get very good fine-tuned ability to see the actual values. We can't compare them with the computations because we lose so much information converting them to 8-bit channel values. So what I want to be able to do is I want to be able to dump to a 32-bit format that I can then, you know, inspect somehow. And I thought about this for a while, how I want to do it. And eventually I decided I want to do this in Python. Python is very easy to do a bunch of different analyses. I can dump the image as a numpy vector, or as a numpy array, I guess it's called. And then I can analyze, you know, the minimum value that I see there, the maximum, the mean, the standard deviation. I can take two different arrays. Like I could take a render, a dump of the depth map, and I could somehow maybe compare that to a dump of the actual depths, and then I could subtract them and see the difference, display that as an image. I could do so many different things. So the first step of that is just being able to dump, learn how to dump. Well, before that, actually, I just did a Hail Mary. I thought maybe the slope scale depth bias, because that generally works with Z depth and we're using distance, maybe it's messing us up somehow. So I disabled it, and spoilers, it didn't change anything, didn't fix anything. So that was a dead end. It was just a Hail Mary. So after that, yeah, I try to integrate C numpy, which is a way of dumping vectors as numpy files. So I found this library online, open source, and I copied in the header in the CPP file. I created a test for it. Test just creates a vector and then uses numpy save, saves it as a numpy file. And that generated this binary file here, which can be loaded from Python, and which does work. The only tricky thing about C numpy was it required dependency on zlib. And I have zlib built into some things. I believe it's built into Asimp, I think. But I don't have it directly as a dependency, and I didn't want to worry about how I'm going to link it all in statically or dynamically. So all I did was I realized that C numpy, it only needs zlib for some functions, and I don't need those functions. So I just removed those functions, and I fixed some stuff up, and I got it to work, and that's it. And it works fine. It works great. I can save numpy files. I can save my vectors as numpy files, and that's it. Now the next step obviously is to be able to dump the, what do you call them, textures or whatever. Want to be able to dump them as numpy files. We're already dumping as images, and there's going to be some duplication of work between dumping as an image and dumping as a numpy file. So what I did was I factored out that part. So I made, let me see here. Yeah. So I create a function here called make staging, which makes the staging texture. And then that can be called from toSurface to create the staging texture, and then that is dumped to our surface. But afterwards, we're going to have another function that is going to, it's going to be called dumpy, because it dumps to numpy, and that amuses me. So that's this one here, dumpy. So how do we do that? Well, we add the function dumpy in depth stencil, and then down here we call make staging. We make that staging texture, and then yeah, we just loop through all the pixels in the texture. This is kind of dumb here. I cast it to a pixel struct that was just left over from copy and pasting, and then down here I reinterpret that back into a pointer to float. There's no reason for that, obviously. So they're both 32 bits, so it works, but I'll probably fix this later on somewhere in the history. But yeah, we just we flatten. What we have here is we have a vector of floats, and we loop through all of the pixels in the depth texture. We flatten that into a single array, and then we call numpy save on that array. We give it the shape, which is the height and the width of our texture. Then in shadow mapping paths, in the dump shadow map, in addition to calling toSurface, we also call dumpy. So we got a familiar scene here. Let me just show you something. Click dump cube map, and we immediately get an error. Cannot find the path specified. And that's just some dumb shit. Git doesn't save directories, only files. So if there's nothing in the directory when I commit, the directory doesn't exist. So now I have to create this dumps again. I don't like that behavior Git, but whatever. We run it. I mean, I could make it so that when I dump, it detects whether the directory exists, and if not, it creates it. But ain't nobody got time for that. So we have our artifact. We click dump cube map. It is going to dump the images and the numpy files. Now we look into that folder, and we see, yes, indeed, we have 6 images and 6 numpy files. So now we got these numpy files, but what are we going to do with them? Well, we want to open them in a Python program. So I'm just going to copy them over here into this folder. I'm going to move them. And then what I'm going to do, let's look at this program here. So we're just going to loop from 0 to 6, well, 0 to 5. And we're going to load the numpy file with that name. And we are going to plot it as an image, just as a 2-dimensional color map or heat map or whatever you want to call it, mapped grayscale from 0 to 1. And see what that does for us. So there we go. We got figure 5. This one looks like it's staring out into the void. Here we go. We've got an image here. And now you can see our, we have our floating point value. If you look in the bottom right here, you can see as I mouse over different parts of it, I can get floating point value at that coordinate, and it's a lot more precise than what we've been getting from our color map dumps. So I imagine this was the one that points straight down. Here's another one that's pointing out into the void. Here's one off to one side. This one seems okay. Distance as we approach here is increasing. Seems all right. Let's close that. This one, distance is small. Doesn't make any sense. Look at this. Distance is decreasing as we move to what appears to be further away from the point light. Yeah, distance is decreasing as we move to here. It doesn't make any sense. This one, as we move left to right, we're not seeing any difference in the distance. Even though, like, let's say the point light is somewhere around here. I guess it would be for this, yeah. Point light is somewhere here, a little further away from the surface. This should obviously be further away than this. But we're getting almost exactly the same distance from here to here, and that doesn't make any sense. It's the same situation here. Distance from here to here, distance from here to here. They're all the same, even though this point should be closer than this point. Or here, this point should be further away than this point. It's not. They're about the same distance. It doesn't make any sense. And let me tell you, I had big plans here. I was gonna, I was gonna dump these maps and I was gonna render to other images and I was gonna compare them and I was gonna do all sorts of processing in Python. But just by displaying these, I already got the answer I needed. Just the ability to mouse over easily like this. All right, now to understand what went wrong, we gotta go back. We gotta review what we're doing and why we're doing it, why we made those decisions. So we're gonna be rendering depth to a cube map, right? You render depth to some kind of texture, and then you use that as a lookup to determine whether something is being shadowed or not. But here's the thing. We're not doing normal depth rendering. We're actually rendering the point-to-point distance, the distance from the point being rendered to the light. And we're rendering that to the texture. Why are we doing that? Well, it goes back to how things work when you do a texture lookup, right? If we're doing a texture lookup, we've got a point here. Let's put it here. It's relative to the light, and that will give us a lookup vector, all right? And that vector can look into the cube texture here, and that is going to give us a depth value. And then we compare that depth value to the depth value of this point. But what's the depth value of this point? Well, if it were, the depth value would simply be this z distance here, right? Z in the space of the capturing of the shadow map. What's that here? Well, for this face of the cube map, the z distance would be this distance here. So we would compare this distance relative to what is stored in the shadow map. But here's the thing. With a cube map, you have a point, but you don't know which face it is going to correspond to unless you do that calculation. When you look up into a shadow map, all you're saying is you give it a vector, it gives you out the depth. You don't know which face. So this point here requires the depth measured in this direction, but this point here would require depth measured in this direction. And that's annoying. You have to figure out which face you're working with and then measure your depth in that direction. Whereas if you store your depth as just a simple distance, point-to-point distance, then it doesn't matter which face it's from, right? It doesn't, because the measurement isn't relative to the projection distance. So in that case, you don't have to figure out which face you're in and then measure your distance relative to that face. You just say, okay, point-to-point distance is this, compare that to what I sampled out of here, and we're good to go. And that is why we're using this length here. Now, second thing, we're taking the length in the vertex shader for each vertex, and then we are interpolating those length values. We're pre-multiplying by W because that gets divided by the rasterizer. That's, it is what it is. It should be fine. But the main problem here is that we are interpolating length. And you might say, well, Chili, you can't interpolate length. Length isn't a linear function. And that's true. You couldn't really interpolate it and expect proper results because it's not linear. The square root of a squared plus b squared plus c squared is definitely not a linear function. But we don't care about actually getting correct results. All we care about is getting consistent results. So if we can get consistency between when we render the shadow map and when we calculate the depth in our Lambertian shader, then it doesn't matter if the results are correct, only that they are consistent with each other. The problem being that they're not going to be consistent and we're going to get like lots of problems. And one example of that is again here, this phenomenon that we're seeing where as we move left to right, the distance stored in this texture stays the same basically. 1.49, 1.5 all the way across. And this is what cued me off to the whole issue because it makes sense when you think about it. We're calculating the distance in the vertex shader and then we're interpolating between those distances. So if the two distances are the same, because they happen to be equal distance from left to right, you're going to see no change in distance between them. Depth is going to stay the same. However, in the code that we're doing in our Lambertian shader, we're getting the positions in XYZ coordinates in, properly interpolated, and then taking the length per pixel. So we're getting, more correct lengths, or the correct lengths basically, in the Lambertian side, but we're not getting that in the side that's generating the shadow map. Now there's a reason why we want to do it this way, right? Because we want to use the hardware features of the shader to do slope scale depth biasing. I mean, I wasn't even sure if it would work with distance depth to begin with, but I wanted to try it. And in order to do that, you have to have the Z in the vertex shader, and then the Z gets interpolated, and then the rasterizer can do the slope scale depth biasing. If we have to calculate the depth, the length per pixel, we've got to put that in the pixel shader, and then we can't get that information out. Once we're at the pixel shader, we're after the stage where we can utilize the slope scale depth biasing. So it's a problem, right? But we see the issue. So basically, for our shadow mapping, we need to create now a pixel shader, and that pixel shader will calculate the length and store that into the shadow map. Now, here's the thing. For our pixel shader, we don't want to actually manipulate the depth, because if you manipulate the depth in the pixel shader, it disables a bunch of optimizations related to, early Z culling, because now the rasterizer can't be sure of the Z value. It might change in the pixel shader. So we don't want to do that. We want to render out our shadow map depth to the red channel in, just a standard render target. So we've got to now enable our engine to support rendering to a render target that is in a cube map. So what I do is in render target, I change this constructor here that takes in an optional face. So now if we pass in a face to this bad boy here, it's going to assume, okay, this render target that is in an existing texture, because we're passing in a pointer to ID3D11 texture. So render target to an existing texture exists within a cube map. And so now if face has value, we are going to, treat the view as texture 2D array, and the slice, the first array slice, is going to be the value that was in that optional, the face, and that's pretty much everything else is the same. So now for our cube texture, we add a new class called the cube target texture, which is a cube texture where you have basically 6 render targets inside of it. So we have a vector of output only render targets in here, and you can bind the cube texture as a cube map, but you can also get render target by index. The implementation of that is pretty much what you would expect. It's mostly just copy and paste from here. Not a big deal. After you create the actual cube map, you are then going to create output only render targets for each face in that cube map, push them back into that vector. So now we've got the new technology where we've got cube maps that you can render to. Cube map render target cube maps. And so now we have the new cube shadow hotness. So in the shadow mapping pass, what are we going to do here? So instead of having the depth cube texture, we're just going to add a normal depth stencil, because we need that for the Z test. We still want to do Z testing and everything. But we're going to add depth cube that is a cube target texture, not a depth cube texture. And the format for this thing is going to be, R32 float. So we're going to have a single element 32-bit float value. That's where our depth is going to be, which is the length, point-to-point length divided by 100. We're going to register that as a source. That will be consumed by the other Lambertian pass. We don't actually have to change Lambertian pass. Even though we've changed this type, it's still compatible. It's got the same name, so it's still going to hook all up into the shader graph. We've got to add pixel shader, shadow PS now. Can't use null pixel shader. We don't need this thing here anymore. When we're rendering out all 6 faces, instead of getting the depth buffer From the depth cube, we're going to get the render target. I'm going to set that as the render target instead of setting the depth buffer. Execute that render queue pass. We'll comment it out this dump shadow map stuff for now because it's not going to work. Probably add it back later. Instead of having the function, the helper function set depth buffer, we're going to use helper function set render target. So when we do this, what is the result? Well, now we see, move our Y, we're not getting that artifact anymore. Now obviously you can see there's pretty bad shadow acne because we're not doing any sort of biasing here. So shadow acne is definitely to be expected, but at least we've gotten rid of the artifact. And there you go. So we analyzed the problem. It was basically because we were interpolating depth or distance between vertices, and you can't do that. Again, to reiterate, if I'm here and I've got vertices here and here, they're the same distance. So if I interpolate two values that are the same, it'll be the same every way across, even though this is obviously closer than this. But that's not how it's going to work when you interpolate those vertices. Anyways, it's not a good fit, because even if you could guarantee consistency within objects, you couldn't guarantee consistency between separate objects. So I think that the approach of interpolating length in the vertex shader is a dead end. Full stop. So again, going back to this commit that I just showed you, instead of interpolating depth, we interpolate the view position. That's the position relative to the shadow camera, which is the light. We interpolate view position, and then in the pixel shader, we take the length of that and we do the division by 100. Now to combat that shadow acne, we could just add a little bit of bias. A little bit of shadow bias in there. And that should clear up that problem. And it does clear up that problem. But I'm not going to show that because in the next commit, I restore the full scene. Now that we've ostensibly fixed the problem, we want to make sure that it still works out in the full scene. And we see that indeed it does seem to be working. Yeah, we've got shadows in all directions here. Just turn up the light a little bit. Yeah, all right. And yeah, you see it. You see it. Full 360 degrees all the way around, double rainbow. And if I move my light now, I'm going to see something pretty sweet. Let me just see if I can do it here. Yeah, move the light. Yeah, there you go. Beautiful omnidirectional lighting from our point light. Omnidirectional shadow mapping, I should say. Now, because we're not doing any filtering, this looks bad, right? I mean, we're doing the hardware filtering still, but we're not doing any, real multi-sample filtering on that. And our shadow bias is kind of high. So you can see a little bit of Peter Panning here. I mean, again, you see a little bit of Peter Panning here. The shadows don't quite line up. This one looks okay. Over here, we're missing shadow here. There should be a bit more shadow, I believe, right there. These ivies here, this foliage should be casting shadows on the pillar, but they're not. Again, that's Peter Panning at work because of our relatively large bias. So I'll try to do a little bit less bias instead of 0.01, 0.005. Honestly, we're still not getting shadow that we should be getting here. The foot looks better. This is acceptable. Not as pronounced as the one before. Now let me show you something here. Because as we turn down the shadow bias, we're going to get self-shadowing shadow acne artifacts. Here's a shadow acne artifact that you get with our length-based depth thing. You get these bands. You get these gradiating bands. And they get worse as you turn down the depth bias. Now, the interesting thing here is when you use just straight depth for your shadow map, not distance, but just depth, a surface is either going to be all acneed or all clear. But with this distance-based thing, it actually gets worse the farther away you get, or basically the angle from the point to the light. So instead of it being based on the slope in the rendering space of the light, it is actually based on the angle point to light. And it's interesting. So here we don't see any of that banding, but as you go in here, it's hard to see, but you can sort of see it here. But when you get the specular going in this direction, you can really start to see it. So it's not too bad. It would be, I would consider this acceptable, in the range of acceptability. But the trade-off is we're still losing shadows. We're losing shadows here. We get some of them, but we're still losing shadows in this foliage, and we're still losing shadows here. So it's not good. What we would like to do is we would like to have our slope scale depth biasing so that we can adjust the amount of bias as it's required. But that's going to be hard because we're not using normal depth, we're using length-based depth. But that's going to be a story for another video. The runtime is starting to crank up on this bad boy. But yeah, I think we did some good work here. You know what I'm saying? I believe that we did do a thing today and it was good. I mean, look at this. This is pretty cool, ain't it? You gotta admit, this is kind of neat. You can see our light going by there. You can see how it casts these shadows here. It's very dynamic. It's a very cool effect. So we solved the major problem. There are still issues left to be addressed. They will be addressed in the next video. But let me know, you guys. Let me know. Because, I mean, it took a while. This wasn't the most organized video. It's basically just me going over some of the things I did, some of the techniques I used, some of the approaches I tried in trying to solve a problem. And, you know, people have been telling me they want to know how you debug. They don't just want to see the final answer. They want to know the process. So I'll try to show you the process like this. But let me know what you think. If you would rather not see it, if you would just rather see the final solution, the final reason, and the way it was solved. You don't want to see the steps in between. I could do that too, honestly. That would be a lot easier for me. But yeah, if you like seeing this little bit more behind the scenes kind of recounting of my debugging struggles, then yeah, I can continue on with the same approach in future videos. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. Helps a lot. And I will see you soon with some more Hardware 3D.